Audio Jungle. Audio Jungle.
Right. So here we have a new topic, which is nothing but torsion and torsion of circular shaft. All right. All right. So torsion of circular shaft. So how to start this? Basically, the basic idea about the torsion. When we'll get the torsion, torsion is basically related to the torque. Okay. Torsion is what which is related to the torque, and torque is what related to the shear force. Sorry, torque is related to the shear stress, and shear stress is related to the shear force. So one by one all sequence I will write here, so you will understand. It can be any shape, but especially here we are going to talk about the circular shaft only. Otherwise this torsion or this torque you can apply, basically this torque you can apply for any kind of the shape, maybe rectangle, maybe square. Okay. So coming to the basic of this, basically if you say torsion, so torsion is nothing but also called torsion is also if it is basically we'll talk about the shaft, then it is nothing but you can write it's a torque. Okay. Or it is also called as a turning moment. One by one each and everything I will explain, just have patience. It is called a turning moment. Turning moment, or it is also called turning moment, also called as twisting moment. These are the different name, but meaning is what? Same. Twisting moment. So these are the different name. Okay. And once this torque or once this twisting moment is what subjected to the shaft, then it is said as torsion of circular shaft. Okay. So basically how you will get the torque. So first we'll see, okay, this torque you will get because of the torque you will get or this twisting moment you will get because of the turning force, okay, because of the turning force. And obviously this turning force is nothing but it's nothing but uh, shear force, and obviously shear force is nothing but also tangential force. Okay. Now you need to relate it. So this when this twisting moment or when this torque, okay, if it is subjected to the shaft, then it is called as a torsion of circular shaft. So when twisting moment or twisting force or tangential force, okay, basically when subjected subjected to shaft, then it is said to be torsion of circular shaft, right? Always remember, whatever this topic now we are talking here. So basically, you see, suppose this is the circular shaft, or as I told you, suppose this is the rectangular shaft also, or any object we have here. For both I am talking. If you see the shear force, suppose for this object, for this object, okay, suppose this is nothing but shear force here. This is the shear force, and when shear force F, okay, this shear force F is what applying. So obviously perpendicular distance will be there, just like here. Now this is the shear force, and obviously perpendicular distance R. So this F, what is the twisting moment? It's a nothing but shear force into perpendicular distance. Is nothing but shear. It's nothing but twisting moment, or obviously it's a torque. Okay. So basically, how this shear force will appear? One, you can say it's a shear force. Otherwise, you can say shear stress also. So once there is the shear stress, suppose shear stress came, then you just multiply uh, by area, then you will get shear force, and multiply by the perpendicular, then you will get torsion. Very simple. So these are the few sequence you need to remember. Okay, if I say, suppose shear stress is what acting here, suppose this is the shear stress, just for example, this is what shear stress, tau, sorry, not sigma, it's a tau. Just say shear stress is what acting here, then how you will get torsion here? So very simple, shear stress means tau. This tau is nothing but shear stress. Okay, right. Then what is the uh, area of this? Area is nothing but shear area or surface area, this surface area. Okay, so suppose shear stress we have a tau into surface area is nothing but A. So you will get shear force. What you will get? Shear force. And this shear force, again, this shear force will be multiplied by the perpendicular distance R. Perpendicular distance R, then it will be torsion or twisting moment. Torsion or twisting moment. So hope you understood the basic idea about the twisting moment, torque, torsion, shear force, shear stress, each and every concept here in short I have explained. Now we go for the theory of this, because I have explained you like how torsion will be there, how twisting moment will appear once you apply the shear stress on the wall of the surface, how twisting moment you will get, how torsion you will get. So this sequence you have to follow. Now first you will have a shear stress, then from shear stress you just multiply by the force, you will get shear force, and to the shear force multiplied by the perpendicular distance, then you will get the torsion, and this torsion is nothing but twisting moment. This idea you know very well, but before going to the derivation of the the formula for this particular, we have to know about the assumption for the circular shaft. Once it is subjected to the torsion, then we should have some assumptions. That point we have to remember. Okay, need to write, it's very important. Assumption Assumptions of shear stress, of shear stress in a circular shaft subjected to torsion. Okay, subjected to torsion. All right. What are the assumptions? You see, material of the shaft is uniform throughout, means homogeneous material. Homogeneous material. Okay. Uh, that property should be uniform throughout the material. Okay. So that's the reason it is said material of the shaft is what should be homogeneous material. Point 2, twist along the shaft is uniform. uh, twist along twist along the shaft is uniform. Normal cross section of the shaft, cross section of the shaft which are plane, which are plane and circular before the twist. Before the twist, what is the mean of its mean is remain plane. huh? It's before twist or after twist that circular shaft will be remain plane. There should not be any bulging and all. Okay, should not be out of plane, it should be in plane. That's the mean of it. Remain remain plane remain plane and circular even after the twist, right? These are the few assumptions, but you need to remember this three. Okay, we have other assumption also, like all diameter of the normal cross section which are straight before the twist remain straight. But if you remember these three, that is more than enough. Okay, now we'll go for the derivation. So first we'll focus on this particular diagram. Suppose now this is what we have a shaft here. Now this is what shaft. One end it is fixed. One end it is fixed now, and once you see, okay, now for this particular shaft, suppose here we have a cross section. Okay, now this is nothing but the axis, we can say vertical from vertical, because we will measure the angular deformation also with respect to the vertical axis, right? So we can mark somewhere and we can say, suppose from here to here we are considering this is the full length of the shaft, and here it is nothing but L length. The length of the shaft is nothing but L. Okay, now we have to apply torque here. This is the torque applied. Okay, this is the torque applied, capital T. Then definitely there will be angular deformation, and that angular deformation we can see by this way. It's very easy to understand. We just focus. I'm considering 2 ends I have to dictate, because once I will apply the torque at this end, so obviously twisting will be there, and once twisting will be there, so definitely suppose earlier this was the point. Okay, earlier suppose this was the point. Oh, sorry. Suppose earlier this was the point, any one point we can fix, and before twisting, suppose here, this is nothing but point A. Once torque is what applied, then this point will be twisted, and it will be twisted by angle phi. Angle phi. And now this point becomes A dash. And this angle deformation, obviously you can see here also at the center of this cross section. Suppose this is the center here. This is the suppose center here. I can mark here. This is the center. So definitely it will be twisted like, so this is nothing but theta. This is nothing but theta. You can see here. So basically, if you check these 2 points, okay, if you check these 2 points, this
Sir, I
point,
can't see your screen.
it's like this is basically cross section, okay, and obviously we have taken cylindrical shaft, so obviously cross section will be the circle, right? Somewhat like here, see. So this is the circular cross section, okay, and if you see the, because once torque is what applied, it is twisted. So points I had considered point A, so obviously it will be twisted by angle theta from the center of the cross sectional circle and becomes theta. Okay, so point is what shifted from A to A dash, and from this end where it is fixed, just say this point is nothing but C. Okay, so this deformation is nothing but phi. This deformation is nothing but phi. So basically our concentration, because this is the full complete shaft here. Now we have to check this cross sections. If you draw this cross section once again, so the cross section will be something like this. This will be the cross section, and from the center of this we have a deformation. It's nothing but 2 points I have to take. This is the point, and this angle is nothing but theta, and this is basically A to A dash. There should not be any confusion. And when it is possible, when there is the torque applied, see, torque applied, this torque is what applied here. All right, correct. So anyway, now coming to the derivation, we can consider this circular shaft, and it is fixed at one end, which is nothing but C, and now we are applying torque at the other ends, just like this figure. So we can write here only we can write T is nothing but torque. This end is what fixed end, okay, this is the fixed end. T is nothing but torque. Unit is what? Newton. Sorry, not Newton per meter. It's a Newton meter. It's a Newton meter. All right. Then Newton meter or Newton mm you can write. It's your choice. And then L is nothing but length. Length of shaft in mm. And R is nothing but radius. We can write radius of circular shaft. Radius of circular. So see, this is nothing but radius r. Okay, anywhere you can write radius r. Now if you check, I have given two angles basically. I have given two angles basically. Okay, so now in this situation we can have angle ACA dash. ACA dash. What is the angle ACA dash now? If you see angle ACA dash, it is nothing but CACA dash. It's nothing but phi. It's nothing but phi, and obviously it will be in degree. And then another angle which is nothing but AO. This one you can say this is O. Okay, this is O. You can say AOA dash. So we can say it's nothing but AOA dash. It's nothing but theta in degree. Okay, uh, theta in degree, or you just take it in a radian. Okay, I'll tell you why. You can take in a radian too, in radian. Okay, now coming to tau, what we have, obviously tau is nothing but shear stress induced at the surface of shaft, obviously, and and G will be the modulus of rigidity. When shear stress will be there, modulus of rigidity will be there. Okay, modulus of rigidity, which is also called torsional rigidity of the shaft material. Right, now we have to focus on the basic of it. You will understand it's very easy, but derivation is very important. We cannot skip. So that you need to remember. Now, what is the shear strain? Okay, what is the shear strain? Shear strain is nothing but, you can say it's a deformation or change in length per unit length. Okay, so basically shear strain also you can write deformation per unit length. Okay, so what is the deformation? You can see here, what is the deformation you are getting. I told you angular deformation we have A to A dash. This is the angular deformation A to A dash. Yes or no? Because of the torque. So it's nothing but A dash divided by what is the total length here. For what length this change was there? It was total length capital L. Right? It was capital L. So A dash by L is nothing but a shear strain. And what is this? If you check what is this value, if you focus this, then this is nothing but, take the triangle here, it is formed in the previous diagram. Better, I'll show you here. See this. huh? So here this angle is nothing but phi, and this angle is nothing but theta. If you just you know relate this 3D diagram, so if you make tan theta, if you make tan theta, it's nothing but, you just see how that triangle will be formed, so uh, it's like, because this will be the perpendicular A dash for this theta, this AA dash will be the perpendicular, right? If you write tan theta, so perpendicular by base. So AA dash is nothing but perpendicular for this theta. And what will be the base then? The complete length will be the base. Okay, complete length will be the base. It's just like this is the AA dash. You think in this way. If you see something like this. So this straight line, if you take, then this is nothing but AA dash, and here the whole length is L. This is what? Theta. In this way you can connect, so you will understand. So obviously this angle, sorry, phi, this is phi, uh, AA dash, sorry, this is phi, but then only L distance you will take, otherwise YL you will take. This is the phi. Okay, just let me correct this part. This is nothing but phi. You check this diagram, you will understand. This is nothing but phi. So it will be LL dash, AA dash, and L. So L will be the base and AA dash will be the perpendicular. The separate diagram, if you draw, then you will get it here. So something like this. I can show you, like this is the A, and here this is AA dash. Right? And where is the phi angle? This is nothing but phi angle. See, this is nothing but phi angle. What is this length? It's nothing but L. Now it is very clear. So if you want to replace AA dash, so how you will replace? What is the tan phi? Check. What is tan phi? It's nothing but AA dash divided by L. So what is AA dash? It's a L tan phi, right? So this is nothing but a strain. Check carefully. This is nothing but a strain. If I will write a strain formula again, is strain. What is strain? Shear strain, na? Because we have a twisting moment. Shear strain, you got AA dash by L. Just now you got AA dash. It's a L tan phi. It's a L tan phi divided by L. Cancel out. What you will have? Tan phi. Lag jayega. Shear strain. What will be the shear strain? It's nothing but tan phi. For a small angle, for a small angle, huh? For a small angle, tan phi you can write as phi approximate, right? Now, so your shear strain, what you have now, it's a phi. Another formula, if you see, of this AA dash, okay, what is the shear strain? This shear strain, if you check, basically you have AA dash by L, and this AA dash is nothing but shear strain. AA dash by L is nothing but shear strain, and this value is nothing but phi now. Yes or no? Now also you can check from here what is AA dash. See, it's very easy. What is the AA dash? This is the arc, this is the radius, and this is what? Theta. So if you check, AA dash is nothing but arc. What is the arc? AA dash, it's nothing but radius into theta. That is very simple. You know, it's a 9th standard mathematics. Arc is nothing but radius into theta, or radius is nothing but arc by theta. Yes or no? Theta is nothing but included angle between A to A dash. So what is R? R is nothing but radius. Theta is nothing but included angle, or theta simple. And AA dash is nothing but arc for this circle. So obviously AA dash you can replace here. So what is the AA dash? AA dash is nothing but r theta. Okay, AA dash is nothing but r theta, and in denominator we have L, and this is nothing but phi. Okay, this is nothing but phi. So obviously, as you know, phi is also shear strain, and as per Hooke's law, what is the shear strain? That you know, shear strain. Okay, shear strain you know very well. What is the shear strain? Shear strain is nothing but uh, Basically, stress is directly proportional to strain, and once you remove the proportionality, you will get modulus of rigidity. So you have stress is equal to strain into modulus of rigidity. Then what will be the stress? What will be the strain? Strain is nothing but stress modulus of rigidity, that is Z. Already I have given formula for the shear stress. So shear stress is nothing but strain into modulus of rigidity, that you know very well. So what is the shear strain? Basically it's nothing but phi, and stress, shear stress is nothing but tau by G. Okay, so automatically here I can write the equation, that is r theta by L. R theta by L is equal to phi, and this phi is nothing but shear strain. Shear strain you can write shear stress by shear stress. Shear strain is nothing but, I can write here, shear strain. Phi is nothing but shear strain, and what is the shear strain formula? It's a shear stress by modulus of rigidity, just like a Young modulus. Rigidity, right? Rigidity. So r theta by L is equal to phi, and phi is nothing but shear strain, which is nothing but shear stress tau by G. All right. This value you will get. So what is the tau by Z here? I can tell you tau by Z is nothing but shear stress by modulus of rigidity is equal to r theta by L. Phi you can now remove, because instead of phi only tau by G we got here. So what is the tau by R? See, tau by R. What is tau by R? Tau by R is nothing but Z theta by L. This is very important result. In examination, obviously this will be very important. With the help of this equation, we will able to find the solution of any problems. Okay, this is the one which is very important. Right. Now, tau by R is equal to G theta by L. As you know, it's a relation between the shear stress and the modulus of rigidity, length, and theta is nothing but that twisting angle also you can say. Okay, twisting angle also you can say theta. Okay, now coming to the next, if you see anywhere, I mean tau by R you have taken, but this tau is basically on the surface of the, I will show you, then you will understand. Check. If I say this is the shaft now, so obviously where will be the twisting moment? Twisting moment tau is nothing but here only. This is the tau twisting moment. So definitely where is the shear stress? Obviously shear stress is what here on the surface of it. What is this? Tau. And this radius is nothing but capital R, about point O. But this can be anywhere. I mean any layer you can take, any radial for a small r distance also you can take. You can say somewhere here, somewhere here. If this radial distance is nothing but a small r, and then what is the shear stress on this layer or on this ring? On this ring the shear stress is nothing but a small tau. So also you can say small tau by small r is equal to capital tau by capital R. That also will work. Okay, always remember, this is very important. This is capital R is nothing but the surface of the, surface of the shaft. Capital R is the radius, but small r is what? Any radial distance. It can be any radial distance. Nothing to worry. Capital tau, or this I can say is tau R, and this is tau capital R. So this tau small r means this tau is the shear stress for small r radial distance, and this tau is the shear stress for capital R radial distance. Capital R means you are on the surface of the shaft, and small r means somewhere inside the shaft, some any radial distance you are taking there. Okay, that should be very clear. There should not be any doubt now. Okay, now coming to this, because the problem is what not solved yet, we have to also calculate that torque. With respect to the torque also we have to calculate the formula, because till now what we have done, we have only define shear stress. Shear stress, we got that relation. Shear stress, r radial distance, z modulus of rigidity, theta is the twisting moment, and L is the length of the shaft. But still we have not derived the twisting moment formula. Okay, so we are now interested about twisting moment formula. So next we can go for it. So it's very easy dear, you just concentrate, you will understand. I can tell you, I just take one shaft here, cross sectional view. I'm just going to derive the twisting moment. Twisting moment. Okay, I'm going to derive the twisting moment here. Twisting moment, that means torque. Anyway, so if you go for the twisting moment, so you just see the cross section of the shaft. Sorry, this is the cross section of the shaft here. This is the cross section of the shaft. What is the radius? Obviously it's from point O. Obviously this radius will be capital R, but I'm taking a small ring here, and that ring is what? Somewhat like this. And this ring is nothing but, obviously if you go for it, it's nothing but a small r. Okay, it's small r, and obviously thickness, if you check for this, so it's nothing but the thickness of it's nothing but dr. Okay, now just focus on it so you will understand. R is nothing but, see, R is nothing but radius of the shaft. Radius of shaft. Tau is shear stress developed in in outermost in outermost layer of shaft. Okay, now you can check. If I want to write, suppose, because I'm interested about the, suppose shear force, so obviously we should know the uh, that area we should know, and shear force will be what? Stress into area. So I'm considering this shaft, and this shaft is what now subjected with the torque, and this torque is nothing but, you say, it is capital T. Okay, right? And we have taken one elements, and this element is nothing but thickness is what? Dr. Obviously we need to calculate the area of this element. So what will be the elemental area here? Elemental area of ring of r radius, and thickness is nothing but dr. So you know very well, if I can write uh, dA, that is the area. If you break this, ring, then how it will be? It will be something like this. See, because thickness is nothing but, this thickness is nothing but dr. Once you cut and expand this ring, then what will be that? It's a 2 pi r. So what is the area? Length into width. So 2 pi is the r, is the circumference of this ring, and thickness is nothing but dr. So basically area is nothing but 2 pi r dr. There should not be any doubt about it. Okay, now if you are writing the stress at this section, which section? R distance. So what will be the stress? Obviously it will be easy. Now stress at r distance, stress at r radial distance means where they are talking about the stress, they are talking stress for this. So what is the stress here? It's a tau small r, right? Just now here I had explained you. So if you are writing tau for that small r radial distance, it's nothing but tau r. What will be this tau r? So this tau r is nothing but the tau, okay? Tau, because tau r by small r is equal to tau by capital R. Just now I have told you here, see this one. So small tau r, what is the small tau r? Small tau r is nothing but tau by capital R into small r. Yes or no? Into small r. Now if I am writing, this is the shear stress. Now I am interesting about the, for same, I am just interesting about the, you know, shear stress we got, but now I am interested about the shear force. What is the shear force for this section? Shear force for r radial distance, r radial distance section. What is the shear force for this? So whatever the shear force, it will be the turning force. Yes or no? Shear force will be the turning force. Turning force means it will try to rotate the shaft. This shear force will try to rotate the shaft. So this shear force is nothing but, I can write F small r. F small r is nothing but tau r into delta dA, that is the area. Okay, so it's nothing but tau by capital R small r into what is the area. Just now you have written 2 pi r dr. This is the area d, 2 pi r dr. Now check stress into area will be force or not. Yes, it will be the force. So we have written here, and if you break and open it, so what will be the shear force? And remember, this shear force is what? For this r radial distance section, means for this one only, for this ring. For this ring we are calculating only, okay? Anyway, so this fr is nothing but what you have written here. It's a tau by capital R. It's a tau by capital R into small r into 2 pi r dr. This is the area. Now coming to this, you just check few things. Will be the tau by capital R will be as it is, and it's nothing but 2 pi r square dr. All right. So also you just take outside whatever the constant, like 2 pi tau by capital R. This is what constant, and r square dr is the. So this is the, you know, turning force, or turning force or shear force for the small ring, for the small ring. But now our job is to find what? Our job is to find twisting moment. And in initial only, if you see, already I had explained the basic of it. What was the basic, like how we'll get the twisting moment? It was clearly explained. If we want torque, then we should have a twisting, a tangential force, and before the tangential force we should have a tangential stress. Okay, tangential stress. So from the tangential stress we have to get force. How? Just stress into area. Here I have given stress into area will be the shear force or tangential force. And how to get a twisting moment? So it will be the tangential force or turning force will be multiplied by the perpendicular distance, then we'll get torque or twisting moment. How will get twisting moment? We have to multiply to this tangential force or shear force by perpendicular distance. So the same thing we are doing here. What we done, we had calculated here the stress. First check, we have calculated the shear stress for that section, and that value is nothing but this one. Now for this ring, basically for this ring which is at r radial distance, for this particular ring we had calculated tau r, and for this ring we also have calculated tangential force or shear force by multiplying the area. Now suppose I am interested about the twisting moment, because that is my final uh, uh, my final goal is what? To get the twisting moment, to get the torque actually. Okay, so how to get twisting moment or torque? by using the formula shear force into perpendicular distance. So shear force now we got here, this is nothing but shear force. Now from the shear force, now if I'm just multiplying the perpendicular radial distance to the shear force, then we'll get the twisting moment. Okay, so from this how we will get the twisting moment? It's very easy. So if I'm trying for the twisting moment, so twisting moment will be, because it's a very small elemental ring, so for that we will have a dt, that is the twisting moment for that elemental ring, and it is nothing but fr into what is the perpendicular distance. Anywhere if you check what is the perpendicular distance, so perpendicular distance is nothing but this is small r, because now here we have tau r. Obviously after the tau r we also get the shear force on this. What is the shear force? It is f into r. So F into R into perpendicular this R distance will give the torque. So what is the torque? Torque is nothing but Fr into perpendicular distance R, and this torque will be the small dt. Why? Because this is for the element only. Okay, and for complete shaft, if you want to calculate, then you have to integrate from 0 to R. That's simple. Okay, it's very easy. So now Fr into perpendicular distance is nothing but R. So what is the dt? That is twisting moment. Just focus here. Now almost it is done. So twisting moment is nothing but for the elemental ring. It is obviously dt, but I'm just going to calculate this torque for the full section. So obviously you have to integrate this, and now you just keep this value. So from where to where you have to integrate? You have to integrate for 0 to capital R, and this dt value you have to write fr into r. If you check, it is 0 to r. What is the fr? So this is nothing but fr complete. You just write 2 pi tau. I need to write 2 pi tau divided by capital R into r square dr we have, but again you have to multiply by r. So it's a r square into r will be r cube into dr. Now it's done. So this t is nothing but you just integrate 0 to t, take common, sorry, not common, constant you take outside. So I can take outside here only. So what is this value? Check what is the constant. It's nothing but 2 pi tau divided by capital R, and now it's nothing but 0 to r cube dr, right? So what is the t? If you see, it's nothing but 2 pi tau divided by capital R. It's a r to power 4, and you put the limit, so it will be capital R 4 by 4. If I'm not wrong, this will be the value, right? So what is capital T? You see R, one R will be cancelled out, so I can cut one R. So here it is nothing but R will be cancelled out, obviously. So what you will have, T is equal to C. It's a 2 pi 2 pi tau divided by 4, 2 pi tau divided by 4 into r cube. This is the tau, or you can set t by tau, that also we can take. Okay, uh, that also we can take here, and this 2 pi, right, pi by 2 if I'm not wrong into r cube, you will have this value. Also I'm interested about the one very important parameter, which is nothing but the polar moment of inertia for the circle. We need to keep that also. What is that? It's very simple. If you write the polar moment of inertia, then what we will do? Okay, so this is the torque, that is okay. I mean torque you got, twisting moment you got, it's nothing but pi tau divided by 2 into r cube. This is the twisting moment you got here. This is the twisting moment, but I just want to simplify this, and I want to relate one final formula. This is torque, it's okay, this one is correct one, no doubt about it. This is the correct one. Pi by 2 tau into r cube is nothing but torque. But if you see, I can do one thing, this torque I can take as it is. Here pi by 2 we have here, pi by 2 we take outside, tau divided by r into multiplied by r. So r cube is there. You just multiply one more r, so it will be r power 4. If you see r cancel out, again r cube you will get. Why I am doing this manipulation, I will tell you. So automatically, if you see, we have a tau by r. We just keep this side, and this side you can write tau divided by all, everything will come in denominator, pi by 2 and r to power 4. It will comes like this. Okay, this is t and this is pi by 2. What is the r radius in terms of diameter? Is diameter by 2 to power 4. Okay, we can write in this way also. It's nothing but tau by r. Just check it what I am trying to do. Now the next page I will write T divided torque divided by pi by 2, and here it's diameter to power 4, diameter to power 4, 2 to power 4 is nothing but I think 416, no? 2 into 2, 4, 2, 8, 16, right. So it is again tau by r we have, tau by r we have. Now see here, it's a T divided by what you will get, pi by 32 into d to power 4, it's nothing but tau by r. Okay, T divided by, this is nothing but j. What is j? Polar moment of inertia, tau by r. So this formula you got, very important. Okay, very important for the shaft. What is j? J is nothing but polar moment of inertia. What is that? Polar, already I have proved this, polar moment of inertia. What is the value of j? It's nothing but pi by 32 d to power 4. This is the polar moment of inertia. So automatically you got T by j is equal to tau by r, and previously we had derived tau by r is also, tau by r is also, here see, tau by r is also g theta by l, g theta by l. Now you can combine this. So tau by r also g theta by l. This is the complete equation of, this is the complete equation of the torsion of the shaft. Everything is what known here. J is the polar moment of inertia, that already I have discussed in my previous lecture. G, modulus of rigidity, theta is the twisting angle, L is the length of the shaft, T, tau is the shear stress, R is the radius, J is the polar moment of inertia. So this is the torsion equation. Torsion equation. Okay, this is the complete torsion equation of shaft, circular shaft, of circular shaft. Okay, of, because whatever the j here you have written, this value is what for the circular shaft. Suppose this is the circle, and for this circle suppose diameter is what, d, then polar moment of inertia j will be pi by 32 d to the power 4. This is for the circle only, for the circular section. That's the reason I have said, if you say this formula, this formula is especially for the circular shaft. Okay, because then only j will be taken as pi by 32 d to the power 4. All right, done.